Hello, this is practical part of lecture 5, and this time I'll show you some interesting task and a real-world dataset. I'll start the model training and explain the task. So it's going to deal with marketing. So we'll be actually predicting payment in a mobile application. Okay, so 1 second. Predicting those users who are likely to pay. So we've got some clients installing an application. I'll have a time access here, and suppose in day T0 somebody installs an app. And we're going to track his or her history for some 8 days and predict whether this guy is going to pay in some 3 months. So let's call this T7 and then T90. So we're going to track user history in these 7 days or maybe 8 days and then predict payment in 3 months. So we're going to track user payments. Well, it's obvious if the guy paid in these 8 days, then he or she definitely paid in 90 days. But we'll also track user sessions and launches. So there is a slight difference between a launch and a session. You can launch an application and it's counted as a launch, obviously, but one launch can consist of several sessions. If you are distracted for some 1 minute or your screen is off, then the next session can start. So one launch can consist of multiple sessions. And so the idea is that if there are no payments, still with sessions and launches we can predict payment in 3 months. So why is it so interesting? With predicting payment, we can then make a scoring, like we already discussed in previous part. So for the training set, we've got targets and we've got model predictions. So actually probability of payment. So here in the top we'll have maybe ones, then other probabilities 0.8, 0.7 and so on till something small. And we've got some real zeros and ones. So the crucial idea here is marketing, is to attract more people into application. And here we can take the top of our rating. So actually for a new, this is the training set with targets. So here we'll be assessing model quality. And in this task, it will be really crucial to come up with a nice metric. So we'll discuss accuracy, precision, recall, and other metrics. We'll see which ones are reasonable here. I'll just describe the business case. So this is the training set, and for test set, of course, we'll have only predicted probabilities. Okay. Of course, we have IDs everywhere. So for test set, we've got user IDs and P plus predicted probability of payment. And we're interested in these top K positions. And actually, Google has an API where you can send this data. So this is some Google Marketing API. Actually, I don't know exactly its name, so I can say it's confidential, but the honest answer is that I don't know. So other guys in this project dealt with it. Google has some model to attract more people like this. So my suggestion is that Google has some lookalike model, and Google sends you back some customers, so some new IDs, which are similar to those that you sent. So it's actually tracked via Google Advertising ID, GAID, Google Advertising ID. So based on these IDs, you send data to Google and get back new IDs. And actually the idea is that if you send Google nice paying users, then Google will find new similar users and you'll actually increase the number of paying users. Okay, so we can wait for some time and wait for actual data, but it's also very nice to look forward in the future and to predict actually this payment. So we'll do it based on predicted probability of payment. So in order not to wait for 90 days. It's really similar to a marketing task of predicting LTV. So it's something similar. LTV is lifetime value. But predicting LTV is a regression problem. Here we're just interested in predicting whether the guy is going to pay. So we'll use this information. Okay, so let's quickly discuss some metric which we can use for this task. So speaking about models, we'll just stick to random forest and logistic regression. So I'll claim that. For models, we'll just use RF and logit. We're not going to tune hyperparameters very much. And we'll see that these models are going to provide nice results. But what are actually metrics here? The question is much more interesting, and it's somewhat connected with the business side of this problem. So we can keep track of accuracy, precision, recall, maybe F-score, area on the curve. So we'll actually see that most of these metrics don't make any sense in this task. And you've seen that we are actually interested in top K positions of this rating. So we'll also study lift. Okay, let's switch to the task. Okay, yep, so actually it didn't work really well. Okay, I'll start explaining the code, then I'll run the model training. So we've got some actual data on user launches, sessions and payments, and more than 1 million rows and about 50 columns. So we've got launches of the application for the first day, for the second, and so on for the 8th day. Then the same for sessions and for payments, and actually a number of payments. Target here will be LTV on 90th day, so it actually nothing different from some payments, so it's just the same, but we'll separate it as a target variable. Typically for such data sets, you've got an imbalance problem. So you see let's check the percentage of paying users. Okay, so the mean target is around 7.5%. So 92.5% of users just don't pay anything. Okay, so here we have time index. So it was dt in this date frame, and you need to make sure that your data is actually sorted in time. So because we've got time index, we need to think of careful cross-validation. Okay, so I'll run the code again. So this will split our data, and I'll describe it in a second. Sorry, I'll just rerun the whole thing. And while it's trained, I'll explain the cross-validation scheme, so we need to be really careful with it. And we'll also discuss why some metrics don't suit in this problem. Okay, so I'm sorting the data frame with time. Then I'm selecting features, sessions, launches, number of payments. So I select all of these, 32 features. Then I split data. Okay, so we've got 7.6% of paying users in a training set and around 7% in a validation set. And we'll try random forest and logistic regression. I'm training random forest of 300 trees. I've parallelized the whole process, fixed random state. And one important thing is to use balanced class weight. So random forest can support these. We've got a small imbalance in our dataset, and random forest can treat instances with different weights. So here, paying users will be given more weight. Okay, the model is going to train for some 5 minutes. So I'll explain further the cross-validation scheme and what metrics are actually reasonable in this task. Okay, so again, this time axis. And a correct cross-validation scheme will be this one. So we'll have some training set and some validation set. And you see this specific that we need some 3 months to actually calculate target. So suppose this is a training set. This is going to be a validation set. But for these guys, in the end of the training set, we took a look at 8 days collecting data on them, but we need some 3 months to calculate actually the target. So we need a gap of 3 months to actually calculate LTV 90 for these guys. And the same for validation set. So if it's this point is today, then the correct train validation split will be this one. So we need some data to calculate target also for the validation set. And if we have more data, we can do it several times, selecting different validation sets. So actually this scheme is crucial because we can have some distribution changes in our payments. So let's say this is a graph of total payments in an application. So it can, maybe it's almost constant in some period, but then you invest much more money in promoting and you've got a spike in payments, and maybe then it decreases somewhat. And so actually to honestly assess your model quality, you need to always keep your validation set in future as compared to a train set. So I'll depict an incorrect validation scheme. So if you take a train set like this, so if it's train and your validation is let's say it's green, so just 2 pieces of your data in a training set and in validation set, then it's no good. So you use your future data from here to predict for your validation set. So you've taken future data here from train to predict in a validation set. So this is incorrect, no good. And the correct validation scheme will be to always keep your validation set in future. And of course, it corresponds to your desire to in the end, to use all of your training data to build some model and to predict, of course, in the future. Okay, so our model is trained. So what do we do now? Okay, so first we'll make a prediction for validation set, forest predicted probes. We'll take this forest and use method predict proba for our validation set. We are only interested in the second column, actually predicting payment. Okay, so it also takes some time for 300 trees, but now it will be done in a couple of seconds. So what do we do now? We can calculate some metrics. We'll take a look at accuracy score, precision score, recall score, and whatnot. So let's, for now, also discuss rock oak score. Okay, we can calculate this thing, rock oak score. We've got actual answers for our validation set, and we've got these predicted probabilities. We've got something like 96.5. The main question is that good? You can actually compare AUX for different models, for different features, but we don't know whether it's good or not. So it's a really serious answer, question, is that good? We actually don't know. We only know that the closer to 1, the better. Let's think about a simple baseline. So in our features, we have payments. Yep. So all these number of payments and sums of payments. And obviously, if some guy paid in these 8 days, then the target is 1. So definitely this guy is also paid for in 3 months. So a very simple baseline will be to take validation set, to take just the feature sum payments on the 8th day. If it's greater than 0, then the guy actually paid. Let's calculate accuracy for such a prediction. So this is going to be our reasonable baseline. Do we do better? So we've got predicted probabilities. So typically, to get zeros and ones, by default you compare it with 0.5. So if we do the same and calculate accuracy for such a prediction, where you take predicted probabilities and compare it to 0.5, that's exactly the vector that you get if you just apply predict for this forest. So here we used predict proba. So predict will compare predicted probabilities with 0.5. Wow, you see that with our model we get lower accuracy. That's really strange. So actually the conclusion here maybe is not that the model is no good at all, but that accuracy can be misleading. And we've discussed it for imbalanced dataset. Accuracy is not a really nice metric to calculate. Okay, so our model, according to accuracy, performed even worse than this reasonable baseline. Okay, what about precision and recall? So for now we discussed ROC-AUG to actually assess the quality of predictions in terms of probabilities. Here for accuracy we compare it typically with some threshold. But now's the time to actually discuss the business task. So we are actually interested only in the top of this rating. So if you think about ROC-AUG, what it actually does. So for our task, it doesn't do really nice job. So we've got this huge long list of all observations in our validation set. So it's we've got about 1 million objects. Let's take a look. In validation set, we've got 350k observations. And ROC-AUG actually depends on correct ordering of our observations. So if you do the same for a train set, so as we discussed, ROC-AUG only calculates mistakes like these ones, where you, for a negative object, you put a higher predicted probability than for a positive object. Let's say it's 0.8, but here 0.7, so it's a mistake, and ROC-AUG can be interpreted as 1 minus the proportion of such misrankings. Okay, and so actually ROC-AUG is also calculated with this long tail of all our observations, but actually we are interested here only in the top of our rating. So let's take a look at lift, another metric. So what we'll do here, let's create this our scoring. So for validation set, we have let's create a data frame. We have true label, answers for validation set. We'll have prediction by random forest. And let's also take this baseline prediction. Prediction baseline. It's going to be just this vector comparing the payment on the 8th day with 0. And let's convert it to int as type int. Okay, call it prediction df, and let's sort the values here by random forest prediction forest, and in descending order. Okay, if we take head of this, so let's first do it in place, and take a look at the head, predicted df head. Okay, so if you take a look at the first 5 rows, so nothing interesting. So the model is correct for all these 5 cases. But let's calculate lift, and here for this business task, lift is much more relevant. So we're actually interested in top performers in this rating. So actually clients that we think are most probable to pay, and we take top let's say 50k, top 50,000, we send it to Google and get back actually clients similar to these 50k. So we'd like to actually to find good 50,000 clients from our rating. So for this we'll calculate lift. We'll take our prediction df and take a look at first 50k positions. Actually, we're interested in share of those who paid in this data set. Okay, if we calculate this, you see in these 50k positions, there are 43% of those who paid. Let's just compare it with the mean target for our validation set. So in our validation set, we had only, in the full validation set, we got only around 7% of this. If we divide one versus another, we got 6.3, the value of lift. Okay, let's calculate the same, but for our really very simple baseline. So here we'll sort our dataset with the baseline prediction. And we again will take first 50k positions. Okay, what we get here is around 40%. Again, if we divide it by the share of paying users in the whole validation set, we've got lift slightly less. Okay, so now we see that the model actually is somewhat relevant, so it's a bit better than baseline in these terms, and lift is actually very well interpreted. So if we send users based on their payment on the 8th day, so with this simple baseline, it's around 5.87, better than just sending random users to Google. But with this model, we can have a slight improvement. So lift answers the question, how better is it to believe in our model predictions, and how much better is it as compared to just sending random data. Okay, so actually this is not all available data. Here we only used sessions launches, and sessions and launches actually helped to predict that the guy is going to pay, even if there were no payments in 8 days. There are much more features that can be extracted. So here we had countries, regions, age, gender, and so on. And a very cool source of features are mobile application specific features, all the logins, all in-game events. In practice, they increase the quality much better. So the most interesting part here is actually lift. Not lift, but in general, the metric. So how do you actually solve the problem? Okay, but let's also discuss this second part. So typically, your solution in your data science task can, so typically it needs to handle some limitations from your business, from your boss, whatever. So let's suppose that a really reasonable limitation would be to keep precision at some level, and we're actually here maximizing recall. Yep. So now we'll explore precision and recall. So you see, actually here we're interested in mostly in recall. I'll comment this. So speaking about metrics, the most important one is recall. But you can't just maximize recall. Otherwise, so in this case, if you just maximize recall, you won't like this solution. So if you set the threshold for probabilities at 0, then you always predict once, and your recall will be maximal. So will maximize recall, but with a limitation that precision should be higher than 0.5. So it's a typical case. So what does it mean? So we'll try to maximize recall, but let's say that our boss asks us that from this top rating that we sent to Google, actually we need to check that at least half of the users are actually payers. We'll see that only in 3 months. So suppose we send some data to Google, and in 3 months we can check whether they actually paid or not. And so maybe it's a reasonable idea just to keep precision at a certain level. Okay, so let's take a look at that. So let's first calculate some precision and recall scores, just in the very same manner as we did for accuracy. So if we use this threshold by default 0.5 and calculate precision scores, precision and recall scores. So let's compare it again for forest and for simple baseline. Okay, so for simple baseline we've got precision of just 1. So obviously here we select only those who paid. One moment, is that obvious? So precision score for such a prediction. Yes, okay, precision, but let's take a look at recall. Okay, so recall is a bit slightly better for our random forest than for this simple baseline. We can actually calculate F-score, but as I said, it's not really obvious how you treat that. So I would say lift is very well interpreted from business side, as we discussed. But as for F-score, again, it can only serve as a for different models, comparing different features, different hyperparameter settings, but how can you actually interpret it? Not a really simple question. So if we calculate F1 scores, we even see that again for our baseline, F1 score is higher, but again, according to lift, we see some really some sense in our model. But we didn't yet tune this threshold, and actually by doing so, we can solve this problem. How can we keep precision at some level and at the same time maximize recall? That sounds really reasonable in our task. Okay, I'll just copy-paste some code from sklearn documentation. We'll build precision recall curves. Okay, precision and recall, we got it. Precision recall curve. Some bug fix. Okay. What we do here, we'll vary this threshold with which we compare predicted probabilities, and then we get some metrics of precision and recall. I'll just illustrate. So let's copy-paste this. So we've got different precisions and recalls for different values of threshold. Okay, let's call this threshold tau, and we'll compare predictions with threshold. And in this way, we've got different values of precision and recall score. So if you change it, you've got different ones, and actually the plot varies different values of threshold, and we've got such a graph. Okay, you see if we okay, so from this plot we actually don't see values of thresholds, but let's take a look. If we set a threshold to a high value, we've got high precision and high recall. What if we do it too high? Okay, at some point recall suffers. What if we put this threshold too low? Then on the contrary, recall is going to be high. Okay, if we put it equal to 0, then recall is very high and precision is very low. Okay, so here threshold is 0, and then if we increase it, at some point the precision is 100% and recall is also reasonable. Let's make also a plot of these values against threshold values. So actually we saved these threshold values here, precision recall curve, also returned values of precision, recall, and corresponding thresholds. And we'll actually plot this one. Okay, so we're interested in an optimal threshold. And by optimal here will mean that precision is kept higher than 1/2, and recall is kept, so actually it's maximized. Okay, so you see this precision and recall threshold. So I set some threshold, so it's really easy to optimize it, but I was a bit lazy here. I just found it previously. So this threshold leaves precision higher than 1/2, and recall is maximized. So actually this 0.94, this is threshold. Okay, so now this graph is shows us precision and recall curves based on the threshold. So on the x-axis is our threshold, so we compare predicted probabilities with this threshold. So here the orange line is recall and the blue one is precision, and black dashed one shows us that we'd like to keep precision at least 1/2. And red dashed vertical line shows us this optimal threshold when you satisfy this requirement for precision but keep recall as high as possible. Okay, and now if we compare it again with this baseline, let's again calculate precision and recall for our reasonable baseline. And you see that for this baseline, precision was absolute, but recall was a bit lower. So you see this trade-off. We can allow having guys who didn't pay in our top rating, but at the same time we are interested in recall. So actually the crucial metric here is recall, and with these actions we can actually make recall higher than in case of our reasonable baseline. By the way, a nice thing to do is to plot the distribution, actually the histogram of the model predictions. At some point it leads to some intuition. So here we've got some distribution. It looks okay. Yep. So most of the guys don't pay at all, and for some guys we've got almost 1 predicted probability and something in the middle. But it looks it's really nice to do so, just to get some intuition. Maybe you see something strange. Okay, now we can take a look at feature importance. Nice thing about random forest that it can provide its own rating of features, as we discussed. And let's take a look at this. Okay, from the trained forest, we can take feature importances. Okay, these are raw values, and we need a bit of work to do it nice. So we'll create a data frame with the feature importance, and we'll have coefficients. Okay, we'll do it like this. This will be our columns, and the data frame will be indexed with just feature names. And we've got feature names in our X columns. Okay, so here is the rating, only that we need to sort values by importance and in descending order. Okay, so here's the rating of features. Maybe now it's not really interesting. So it says that the most important features are payments on the 8th day. So not really surprising. Then day 7, then day 6. Sessions and launches on the 8th day are also important, but not that much. But overall, you see that of course payments are more important than launches and sessions. But still, launches and sessions help us a bit in a case when we've got a user who didn't pay in these 8 days, but based on sessions and launches, we can make sure that we actually guessed that this guy is going to pay in 82 days more. Okay, I'll also show confusion metrics, so it's also nice to take a look at these. So I'll again copy paste some code for nice visualization of a confusion metrics, and maybe we'll need some libraries for that. One moment. Okay, so let's build a confusion metrics for our reasonable baseline. So actual labels are y-valid. Predictions will be again x-valid. We'll take a look at the 8th day. Okay, and classes will be, actually classes are stored in the very same model, forest. It has attribute classes. Okay, and we need to import a confusion metrics from sklearn. Okay, so you see these confusion metrics for our reasonable baseline. So we don't make such mistakes then that we predict 1 if actually the true label is 0. Okay, let's think about it. So based on the prediction made only by day 8, if the guy eventually didn't pay, we don't say that this guy is going to pay. So if we see, okay, so if we see that the guy paid in these 8 days, then it's obvious that he or she also paid in 90 days. Okay, but we've got some more errors of this type. So when the true label is 1, but we predict zeros, so it's a false negative. Yeah, so sorry, the confusion matrix is not the very same one that I wrote. Yeah, we see zeros and ones interchanged. Okay, so this type of an error is false negative, and we've got some 4,000 of such errors. And let's do the very same for our random forest predictions. So first, we took predicted probabilities by random forest and compared these only with the default threshold of 5. Okay, and you see in this case we had a bit just a bit less false negative errors, but also some false positives. But when we tuned the threshold, we had it equal to 0.9. Sorry, 0.184 as far as I remember. Yep, and okay, so we claimed that we care about we only care about precision, so that we keep it at least 1/2. So we allow for much more false positives. We claimed that it's not such a big deal. But with this, we decrease much more the number of false negatives, and we are actually interested in finding more true positives. So that's the matter. So you see, with this approach, with a simple baseline, we found a bit more than 20,000 users who paid. And with our model, we find more than 21,000 of those who actually paid. So this is the main motivation in this task. And now let's just do the very same for logistic regression. So typically I compare these two models. So we'll, okay, just not to confuse stuff. Okay, some copy pasting, not a problem, but we'll do the very same for logistic regression. In a real application, it totally depends on the available models. So whether to use logistic regression or random forests, I would say it depends on the model that you use. So you might have a really nice implementation of gradient boosting, and so you'll most probably you'll stick to that. But if you've got nice implementation of a logistic regression, then just go for it. And let's check logistic regression as well. Okay, so from here we'll start logistic regression. I would say that in this task there's actually not feature engineering and model selection is not that crucial. So the main goal is actually to understand the task and to come up with a nice metric. Okay, for logistic regression, we'll need to scale features. So from sklearn preprocessing, we'll import standard scaler, and we'll have xtrain scaled. So first an instance of standard scaler. So we'll feed it with our data and we'll use feed transform to return the result. So it's trained on the training set, and the very same for validation set, but we only use transform there. Okay, and it's going to be x validation scaled. And of course we'll have our model, so logit will be an instance of logistic regression. And again, we'll parallelize the training, we'll fix random state, we'll use balanced class weight. And we'll pick a solver, so there are lots of available solvers, not all of them can be parallelized. We'll take a look at the solver that can be parallelized. Okay. Now we'll train logistic regression with our scaled data. It will require some time. Okay, I will wait a bit, maybe a couple of minutes. Meanwhile, we'll discuss our plan. So it's nice to also try logistic regression here, because we might add much more features in our model. So these features that I showed you, launches, sessions, and payments, so these are only basic ones. In this dataset, you see we've got countries and regions, so we can build a bag of countries, bag of regions. Age and gender might help, but with typical data, you've got lots and lots of missing values here. The most important source of features might be actually sparse. So logistic regression works really well with sparse features. So let's try, maybe it works here. So what features actually help here in this task is actually some in-game events. So I'm not revealing what these events are, but we can build a big bag of events. So event 1 and so on. Event, a typical value will be some 10,000. And for each user, for each ID, we'll just calculate the number of events given, which occurred in these 8 days. So this will be just counts. And you see again this idea of bag of words, and we'll just stack our features, our sessions and launches. We'll just put these features to the right, and then we'll predict this payment. Okay, we are not doing this right now, so I'm only showing you sessions and launches. But a really nice source of features is going to be some in-game events. I'm calling this in-game because actually this application is a game, and in a game you've got some actually events. A user can buy something or can achieve some level, or even clicks somewhere, and so on, log in, log out. So lots and lots of application actually events, and you can also make good use of it. Okay, we've got logistic regression trained. Let's take a look at predicted probabilities. So we'll build a histogram. Okay, so the histogram looks nice, but you see logistic regression predicts exactly one much more often. I would say scaling features here is crucial. When I forgot to do so, I had a really strange distribution of predicted probabilities. So it's really important to do so. to build this plot of predicted probabilities. Okay, Rock-Oak score, you see for random forest it was 96 and a half. Okay, for logistic regression it's a bit lower. Within accuracy is misleading here, but anyway I'll refactor it. Okay, we've got really bad accuracy for logistic regression. Okay, let's take a look at lift. Okay, just refactoring. And we've got lift, well, it's a bit lower. So we see in case of logistic regression, okay, no, it's just a bit higher than this reasonable baseline. But what about precision and recall? Okay, I'll skip this part with not tuned threshold. Let's build the very same precision recall curves for logistic regression. Okay, so actually very strange. So the precision is so low. So maybe some mistake here. I'm just thinking. Okay, but anyway, we'll go for random forest because actually okay, I'm a bit slow with this because I got reasonable results with logistic regression, but at this point I'll just comment that anyway we'll go for random forest here. So because typically if random forest works, then if you tune gradient boosting, you can just use gradient boosting. It's going to be much faster, both in terms of memory and speed. Well, when your dimensions get really very high, then you'll think about dimensionality reduction, maybe with PCA that we're also going to cover. But based on this example, we'll stick to random forest, and we also discussed metrics here in these tasks. And I hope that discussing this business side of the task was also very helpful. Okay, so good luck. Good luck with competitions and with assignments. In assignment 5, you'll take a look at random forest and logistic regression, and you'll again see pros and cons of both algorithms. I will only say that on mlcourse.ai assignments, you see all assignments in our course, and now the deadline for random forest and logistic regression is November 11, and also beating baselines in a medium competition. It's on regression. It's November 18. Okay, so but speaking about lecture 5, so here are two tasks: credit scoring and movie reviews classification. I think this assignment will actually let you get this intuition whether random forest is preferable or linear models like logistic regression. Okay, good luck.